Generate public keys and private keys, RSA algorithm is used with prime numbers 11 and 7. Calculate the value of D if the value of E is chosen as 13. So there is a procedure for this. Here, for example, solution let us take. Let P is equal to 7 prime numbers, Q is equal to 11. Then we can select N as product of two prime numbers, N into 7 into 11, it is 77. So pi will be selected in this procedure as P minus 1 into Q minus 1. So this is nothing but 6 into 10. This is 60. So we have to select E. Already E is chosen as 13. Okay. If E is chosen as 13, then what should be the D? So select E such that we have to select E value such that LCD of pi comma E is equal to 1. Okay. Pi comma E is equal to 1. Already pi we know. So 60 comma E is equal to 1 LCD. Least common divisor. So here we have to calculate D such that DE mod pi is equal to 1 like this. So this will be if you take the 60 for remainder 1, then 60 k plus 1. We have multiply 60 with some k value plus 1. This can be different values. You can have 61, 121. When you take a k value to 3, 181, 4, 1 like this, 241, 301, 306 and so on. Again let us take the samples 306, 301, 361, 421, 481 up to 8, up to k value 8. Okay, select from the above which is divisible by 13. Among these, what is the thing that is divisible by 13? Okay, so because here E value is 13, no? That's why we have taken E value is already chosen as 13. The thing that is divisible by 13 will be D is equal to 481 divided by 13. So 37. So D value should be 37. Option C is the right option here.
Let P of lambda be the characteristic polynomial. This is for let P of lambda be the characteristic polynomial for an n by n matrix A. If lambda is equal to 0 is a root of P of lambda, then which of the following statements are always false? First statement is A as n linearly independent eigenvectors. Second statement, determinant of P of A is equal to 0, and third statement is A is invertible. So let us solve this problem by taking one example. Let us take A as a 2 by 2 matrix. Let A is equal to 1 0 0 1 0 0. So this is 2 by 2 matrix. So here n will be 2, and let us find eigenvalues for this equation, for this matrix. For finding eigenvalues, we equate the determinant of A minus lambda is equal to 0. So if we find this one, we can so here determinant of 1 minus lambda, A minus lambda will be getting as 0 0 minus lambda is equal to 0. So if we solve this one, minus lambda into 1 minus lambda is equal to 0. It implies lambda is equal to 0 comma 1. So the eigenvectors are 0 comma 1. So if 0 comma 1 are eigenvectors, eigenvalues, then we'll be getting eigenvectors as 1 comma 0 transpose and 0 comma 1. So these two are the eigenvectors. If we see these eigenvectors, we can clearly say that these two are linearly independent. So here statement 1, it states that A as n linearly independent eigenvectors, where n is the order of the given matrix. So here n is 2. We have seen that it if we take we have already taken 2 by 2 matrix and we got 2 linearly independent eigenvectors. So we can say that this is true. So now the second statement, determinant of P of A is equal to 0. Second statement, determinant of P of A is equal to 0. By Cayley-Hamilton theorem, every matrix has to satisfy its characteristic equation. So if we substitute that particular matrix in place of lambda, then that equation should be satisfied. That means P of A, as P of lambda is equal to 0, then P of A should also become 0 matrix. So 0 matrix. If this is 0 matrix, then determinant of this matrix will be 0. So we can say that statement 2 is also true. Here statement 2 is always true. Statement 2 is always true but first statement, A has linearly independent n linearly independent eigenvectors. For this example we got this as true, but for some examples, if you take another example, it may not be true. But so we can say that statement 1 is sometimes true, but we cannot say it is always true. Here the question is, we have to identify the statement which is always false. So both 1 and 2 are, eliminate 1 and 2 from the options. So let us go to third statement. A is invertible. In matrices we have a property that sum of the eigenvalues must be equal to trace of A, and product of the eigenvectors should be equal to determinant of the matrix. Here it is given that if lambda is a root of P of lambda, that means 0 is one of the, here 0 is one of the eigenvectors. 0 is one of the eigenvectors. So implies product of eigenvectors will be 0. Product of eigenvectors is nothing but determinant of the matrix. So we can say that determinant of the matrix is always 0 in this case. If determinant of the matrix is 0, then there will not be, we cannot find inverse for that matrix. So here statement 3 is A is invertible is always false. So here correct option is option C.